We covered why we operate or why we need high voltage at the beginning of the course. It's because by running at high voltages, we use less current. It comes with other problems though, is that you've already seen it, that you actually get breakdown in gases, solids, and liquids at high voltages. So we need to test our equipment such that we can show that our systems will operate at high voltage. So this is very much about testing systems as opposed to transmission or distribution. Right, I've given a couple of notes there about AC and DC, but again, we're concentrating on the test systems. The other interesting thing that we look at is that we look at transient high voltages and high currents. Remember that AC transmission lines or DC transmission lines, they're exposed to the environment, and things such as lightning, which is a very high discharge of current over a short period, that will lead to over voltages or over currents, and that affects our system. And because our HV equipment is installed on these exposed lines, they need to be able to perform in that environment. Switching over voltages are something interesting as well. We just touch on it in this course, and then we touch on it in high voltage too. So simply switching your light switch at home. I'm not sure how many people this has happened to, but sometimes you get a bit of a flicker. So there's a transient over voltage there. And that's fine for low voltages because normally it's not high enough to cause problems. But when you start looking at high voltage systems and you close a circuit breaker onto a big transmission line, these switching over voltages move up and down the line. You've tackled traveling waves elsewhere, and that causes additional issues. And we need to account for that. Right, the table that I'm showing here, it's the standard system voltages according to the South African national standards and the international standards. On the left, you've got the nominal voltage. It goes from 11 kV to 765 kV. So that nominal voltage is your three-phase voltage, which is your phase-to-phase voltage or line voltage. The phase-to-earth voltage, you would take that 11 kV and divide it by square root of 3. So you'd come out with around 6.3. We specify a maximum normal maximum voltage that can occur on the system, 12, 24, 36, etc. Our power frequency withstand voltage, that's focused on the equipment that you install on the system. So to be at 28 kilovolts phase to earth voltage that a piece of equipment needs to withstand. Our lightning impulse withstand voltage is 75 or 95. It depends on where you install it. So that's your lightning over voltage. The reason that this is much higher than the power frequency withstand voltage is because there's a difference in how long the voltage is applied to the system. So the lightning impulse, lightning, it's a quick flash, so it's in the microsecond range, whereas the power frequency is in the millisecond, tens of millisecond range. And again, we don't tackle too much with the switching impulse, but we generally tend just to worry about it on the bigger transmission lines. Again, we'll see that the duration of that is a little bit longer than the lightning impulse. That'll come out later. Right, so we're going to start with DC generation. High voltage DC is used for testing of HVDC equipment. It can be used in some sort of medical equipment as well. It's previously been used for testing of HV cables, but the oil paper cables, not the XLPE. It's no longer acceptable for the XLPE. It can be used to charge impulse generators, which we'll come to later. There are industrial applications such as electrostatic precipitators, and of course, transmission. We again are tackling more the testing of HVDC equipment. There are some older generators, such as the Van de Graaff generator. You may have done this in physics at some stage, where there's a big dome and you put your hands on it and your hair goes spiky when people run a system. But we tend to base everything on rectification. So with the diodes type system, as it's easier for us to work with. There's a couple of voltage definitions. So our DC voltage is defined by the DC voltage over a period of time. And we'll see why a little bit later, is that we don't always get a smooth DC waveform. And then the ripple is defined as Vmax minus Vmin divided by 2. So that might be a little bit different to what you do in power electronics. Right, I'm going to stop there, and I'm going to talk about a simple device that we should have seen before. Right, so this is a half-wave rectifier, and I'm just going to walk you through this before I go to the annotated notes. We've got a source. I've said that source has an amplitude of 10 kV. It's got a frequency of 50 hertz. Generally, we're converting with 50 hertz. It's available, so we use that. We've got a diode, and then we've got a capacitor. So let's run this and just see what we're getting. Right, you're all happy that I'm getting 10 kV peak there, 7 kV RMS. Let's have a look at our outputs. So our output will be across the capacitor. Let's run it. Right. It's actually below the capacitor because the direction of the diode. But you're happy there, that green line is indicating 10 kV. Right. Let's have a look at our voltage across the diode. Right, that looks a bit odd, doesn't it? You've got your AC waveform down here. You've got your DC waveform at the 10 kV mark. Let me just run it for a bit longer so it gets smooth. And then you've got this other waveform all the way down here. Right, so that diode actually needs to handle twice the voltage that you're converting at. Otherwise, it's going to have problems. I just want to turn the diode around. That's better. Right, so that's a bit better. There were separate plots. But you can see that DC is just at the peak of the AC waveform. If we look at this, Right, there's definitely an issue there. There's definitely an issue there. So if you look at the voltage from that point to that point, at say this time, you can see that there's 20,000 volts across it. And that's an issue. That's called a peak inverse voltage, and the diode needs to be rated for that. Let's have a look if we connect a load. Just from previous circuits, if you've got a charge capacitor and you connect a resistor in parallel, the current should flow from that capacitor to that load. So let's have a look and see what happens. Right. So over here, you can see this green waveform is the voltage of the capacitor and the voltage of the resistor. It charges up to the peak voltage. As the AC waveform is decreasing, the capacitor discharges into the resistor. You can all see that clearly. Right, so that's why we define our voltage like that, as opposed to just defining it as the peak. Right, I'm just going to have a look at the currents as well. Right, what you can see here in the blue is the current going through the resistor, and it will correspond to the voltage and the discharge of that resistor. And what you can see in the pink is the current coming from the source to charge up the capacitor. So that's a little peak of current as it charges. So it's important to know that, because these components have set ratings. You get a 10 kV or 20 kV diode, but it'll only be able to handle 5 milliamps. If you look down here, we're actually higher than that already. So that's a problem. Right, so if you go and have a look at the annotated notes, we start with our VAC in blue. Here it is here. We can look at our VDC in red. Here it is here. You've seen that already. It charges on the way to the peak, and it discharges when the waveform, with the gradient of the waveform goes down, charges up again, discharges. There we can have a look at our definitions. So there's our ripple. Vmax minus Vmin is 2 delta V. And then our VDC will be the average of that waveform. If we look at our point number 1, at T1, you can see the voltage difference between the capacitor and the input. VDC minus VAC is approximately equal to 2 VDC. So that diode needs to handle 2 VDC. If we have a look at our current is the current flowing through that diode. There's a little peak that occurs as the capacitor charges. And that current needs to be either below the rating of the diode, or it needs to be, or there needs to be a large or a resistor to limit that. So we can actually put a resistor in here to limit the current flowing through there. Right, so the number one point for design, the V diode is equal to 2 VDC. And I've stated that already. So for a 40 kV DC generator, the diode rating needs to be 80 kV. For the current, the diode needs to have a high enough current rating, or it can be used as a current, or you can use a current limiting resistor. And you can just use that equation there. There's some little notes about operation that you'll need to understand. So once charged, VDC is constant if there's no load. Again, if I open the circuit and just look at the voltage here, there it is, it's charging up. Right, so when there's no load, it's a constant DC. If the circuit is loaded, charge is transferred to the load from the capacitor. That charge is equal to the load over time, the current of the load over time. You can integrate that. Effectively, you can convert that current to voltage and resistor relationship. You know that's constant. That's also equal to your average current, your DC current, times your period of your waveform, which is equal to I over F. So I divided by your frequency. Right, the charge transferred causes the ripple. So Q would be equal to 2 delta VC, which is equal to IT. So your ripple is actually given by the relationship I over 2 FC. So those are important things to note. We can look at our full wave rectifier. It's the same concept, but in this case, we center tap our source. So we got VAC there and minus VAC there. And we just, so the voltage across your capacitor, VDC, will be a combination of the converted VAC1 and VAC2. The advantages of this, the total ripple is less, but voltages VAC1 and VAC2 must be balanced. Additionally, there's some extra design work to make sure that you get it right. So there is a question here, what should the voltage rating of the diode be? Is it the same as previously or not? Right, we're going to have a look at the voltage doubler in the same manner as we did this one. Right, we're going to start with our AC source again. We've got a 10 kV source. We've got a capacitor over here this time, and then we've got a diode arranged from earth to your high voltage. Right, so let's maybe have a look at the voltage across that diode. Right, so the red there is your voltage, your 10 kV. Then your yellow is. It's almost the same wave shape, but it seems to be offset by a DC. So remember previously with the half-wave rectifier, when it was fully charged, it didn't discharge. So it's the same case here. And we can have a look. When that capacitor is charged, it can't discharge anywhere. So it basically offsets this waveform. If you think about it logically, you've got your red there and Kirchhoff's voltage law. The point here should be the sum of that plus the sum of that. Right, so that makes sense. It's an offset AC waveform. So that offset AC waveform is not actually useful to us yet. We're doing this system to make a DC system, to make a DC voltage. So let's add a half-wave rectifier on top of that offset point. Right, so as soon as we add a half-wave rectifier, you can see the blue line there is now at 20 kV from your original peak. So we've doubled the original peak voltage. Right, so the question would be, why would we do something like this? And the answer is that we don't know the size of these components yet. We don't know if we get components big enough. So say we've got 20 kV diodes. We can arrange it like this so that we get 20 kV peak out. We don't know if we get 40 kV diodes, etc. So we're doing this so we can build up a DC voltage using components that may be available. And we'll see in the next lecture, when we look at the Cockcroft-Walton, we can do this, we can extend these stages nicely because we can use components that are readily available. Let's just look at a couple of last things. If we put a load onto that, again, you can see the voltage at the output, the purple, it discharges as well. What is interesting now is the shape of the voltages across the circuit. And again, we'll look at it a little bit more in the Cockcroft-Walton. Right, so if we go back and look at our circuit, if you look at your voltage AC, we know that capacitor, if there is no load, there's no discharge to any load, the charge in that capacitor will be the same, and that's because of that diode there. It blocks any current discharging. So the voltage VDC will be the sum of VAC plus VC1. So your voltage across your diode will again have, it'll be necessary to double the rating. If we then add a half-wave rectifier, we can get a smoother output waveform. And again, if we draw a load, we're going to get a ripple. Again, that's explaining how it works. Right, that's as far as I wanted to go today. There was probably, again, quite a lot of information that you need to take in. I would suggest you go and just review what I've done, and then maybe you can post some questions to me that I can post to either the Moodle board or the team that I can respond to.